Okay, so now we can start. Let me share my screen. Okay, can you see it? Okay.
Not yet. Yeah. Yes. We
okay.
can, yeah.
Okay, great. So, okay, so let's begin. Today I'll be talking about some joint work with Brian Brubach, Darshan Chakrabarty, John Dickerson, and Arvind Srinivasan. The title of this paper is Fairnes, Semi-Supervised Learning and More, a general framework for clustering with stochastic pairwise constraints. A bit long of a title. So this paper appeared in AAAI this year, and you can also find the full version of the paper available online in arXiv. Okay, let me begin with a brief discussion on what exactly a generic metric clustering problem is. So in this family of problems, the input includes a set of points C and a set of locations F, where C and F are not necessarily the same. In addition, these two sets are embedded in a metric space, and the metric space is characterized by some distance function D. Finally, the input will also include a positive integer K. Now the goal is to choose a set S of at most K locations, and also construct an assignment function phi that maps every point to one of the chosen locations, such that some objective function is minimized. You can think of S as the set of chosen cluster centers, and of phi as the function that assigns each point to its corresponding cluster. Now, the three most well-studied objective functions in the literature are the following. The first is the K-center objective function, in which we try to minimize the maximum distance of a point to its assigned location. Then we have the K-median objective function, in which we try to minimize the sum of the assignment distances of the points. And finally, perhaps the most popular objective function is the K-means one, in which we minimize the sum of the squared assignment distances of the points. So now I'll start discussing fairness, since this is the topic of the seminar. Fairness in general in machine learning and algorithmic design has received a lot of attention recently, mainly because of the realization that very frequently algorithms have unfair outputs. And there may be multiple reasons for that. So for one thing, the algorithms may not take fairness explicitly into account, so they tend to sacrifice fairness for the sake of optimizing some objective. Another reason may be that the algorithms are trained on datasets that include implicit biases, so the algorithms learn and perpetuate those biases. Examples of such unfortunate events where we have unfairness in algorithmic outputs include, among others, racial bias in Airbnb rentals, gender bias in Google's ad settings, and discrimination in housing ads in Facebook. Thankfully, to some extent, all those problematic situations have been fixed. There have been suggested solutions. However, we see that fairness is of utmost importance and should be taken explicitly into account when we design algorithms, and this is our firm belief here. Now, regarding fairness in clustering, most prior work has focused on a notion of fairness which is called demographic fairness. Now, according to this notion, the input set of points is partitioned into groups or otherwise called demographics. And what is required is a fair treatment or a fair representation of those demographics across the final clustering solution. However, in our work here in this paper, we are interested in a different notion of fairness, which is called individual fairness, and which was first introduced in the seminal work of Duarte et al. Now, according to this concept of fairness, in a clustering problem, we will also have access to an additional metric which will describe the true similarity between pairs of points. And this new metric can be significantly different than the metric space D, because the latter may, for example, encode redundant features such as race or gender. Given this new metric now, the similarity metric, the goal is obviously to treat similar candidates similarly. Before I proceed to our model and our results, let me first make the difference.
Leo, excuse me. Can I make a small point in the spirit of people being able to ask questions or make comments? So just for the people here, so one can ask, but how do you come up with this distance metric between people or similarity metric? There are some works, for example, Cynthia Dwork, she has a student, Christine, I think her first name is Christine, I may be getting it wrong. Last name is Ilvento, I-L-V-E-N-T-O. She has some interesting work in the last few years on trying to infer some kind of similarity metric.
Yeah, I mean, even in this paper, Dwork and al. Discussed the difficulty in coming up with this metric, the true similarity metric. And different people have different interpretations of that metric. I mean, in our experiments here, we use some specific similarity metric, and it's just our way of viewing this. Okay, let me continue. So I'd like to make the differences between demographic and individual fairness clear before I proceed to the model. So as I've said, in demographic fairness, we care about fair treatment of a demographic, but with respect to the other demographics. So for example, we may ask that each demographic's presence in a cluster should be representative of that demographic size across the whole input. Or we may ask that all demographics should be proportionally affected by the properties of the final solution. In individual fairness now, as I'd like to think about it, we go one level deeper. So if we have, let's say, two individuals that share the same overall characteristics, then what we want is to provide the same quality of service to both of them. And this should be regardless of external demographics or external groups that these individuals might belong to. And a good example for that is housing loans. So suppose that we have two applicants with the same profiles. What we want to do is to give them loans that have the same terms. If we don't do so, then the individual that gets the loan with the worst terms would arguably feel unfairly treated because that individual sees its profile, sees the profile of the other individual, understands that the two profiles are the same, so naturally asks the question, why am I treated like that? So there is obviously unfairness in this situation. Okay, so now let me tell you how we took this abstract notion of individual fairness and we transformed it into a rigorous and well-defined computational problem. So as I said, in a clustering setting, this notion of fairness implies that we have access to this similarity metric, this additional similarity metric. So let's say that for a pair of points j and j prime, we have a value psi j prime that is an estimate of the true dissimilarity of the 2 points. So basically the psi value is 1 minus the similarity. And the smaller this value is, the more similar the 2 points, and 0 obviously in this case indicates absolute identity. So the question that someone has to answer at this point is, given those psi values, what can be interpreted as unfair treatment? Well, if we stop and think for a moment, we will see that separating the 2 points, that is placing 2 points in different clusters, implies that we're treating the points differently. So for 2 points that are fairly similar according to the psi metric, deterministically separating them in every run of the algorithm sounds like a bad idea because deterministically we will be treating the points differently, and this can be interpreted as unfair treatment. Therefore, our answer, our way of modeling and interpreting individual fairness in this case is through randomization. And we do that by seeking solutions that would cluster j and j prime apart with probability at most their psi value. So for 2 points that are fairly similar, 2 points that have a small psi value, the probability with which they will be placed in different solutions and they will get different treatment will be small. So this is just our way of interpreting individual fairness in this case, and this is through randomization. Now I'd like to show you the formal problem definition. So in our model, the input of a standard clustering problem is augmented in the following way. We are given a set P that contains pairs of points, and such a pair may be JQ and JQ prime, for example. And for each such pair, we are also given a value psi q that corresponds to the true dissimilarity between those 2 points. I'd also like to mention that we don't necessarily have to know all different psi values for every possible pair of points. In the model, we assume that we are working with an explicitly given list of pairs of points. Now, what is our goal? Of course, again, we want to choose a set of locations S with cardinality at most K, but this time we don't just want a single assignment function. We rather want a distribution D over assignments, and those assignments will be using the set of chosen locations S. And the properties we want our solution to satisfy are the following. We want to be able to efficiently sample an assignment from that distribution, and by efficiently, I mean in polynomial time. But most importantly, we want this distribution D to satisfy the solution to satisfy what we call the bounded separation probability constraint, or BSP for short. And basically, this constraint exactly captures the concept of fairness we aim to study. And this constraint says that the probability with which a randomly drawn assignment separates two given points will be at most the provided psi value for the 2 points. Finally, we also want to minimize some objective function, some metric-related objective function. So in the case-centered case, this means that we simply want to find the minimum value tau, such that every point is assigned to a location within distance tau from it, and this should hold with probability 1 for all points. And in the k-median and k-mean cases, we want to minimize the expected value of the random variable that corresponds to the objective function study. Obviously, our problems here are NP-hard, and this is because they are straightforward generalizations of already known NP-hard problems. I mean, all case-centered, k-median, and k-means are known NP-hard problems, and what we study here is basically those standard clustering problems with one additional constraint, which is the BSP constraint. So this is the formal definition for our model. Now let me discuss connections to previous work. And at first I'll discuss connections to one of our earlier papers, which actually appeared in ICML 2020. In that paper, we studied a very similar setting in which the objective function was the case-centered one. And we also had BSP constraints, the same constraints. But in that work, for every pair of points, the psi value for the BSP constraint was said to be the distance of the 2 points over some given parameter alpha. The result there in that paper was a scalable log K approximation algorithm, which also satisfied very, very strong guarantees on some community preservation properties. And finally, that algorithm also enjoyed the bounded price of fairness. And for those of you that are not familiar with the term price of fairness is basically the ratio of the value of the optimal fair solution over the value of the optimal unfair solution. So the price of fairness is basically a metric that measures how bad the objective function gets when you incorporate fairness constraints in any problem. Okay, so that was our earlier result. Now, compared to that, our current work can also handle the k-median and the k-means objectives. And admittedly, these are the ones mostly used in practice, especially the k-means one. Also here for the BSP constraints, the psi values can be arbitrary and not just some fixed function of the distance. Here we also provide constant factor approximations, but the algorithmic approach we use here is LP based, which means that the results here are not really that scalable. Also, we aren't able to provide strong community preservation properties. The community preservation properties we give here are a bit weaker. And finally, we weren't able to provide any guarantee on the price of fairness in this paper. Now, another paper that is closely related to ours here is that of Anderson et al. And that paper is related to our work here because it also studies a stochastic notion of individual fairness for clustering. And the goal there is the following. They want to choose a set S of at most k locations, but for every point j, they wanted an assignment distribution phi j over the set of chosen locations. And by that, I mean that this distribution phi j will contain a probability phi I comma j for assigning point j to some of the chosen locations I. So they want this assignment distribution. And the way they see individual fairness is the following. For two similar points, j and j prime, they want to make sure that the assignment distributions phi j and phi j prime are statistically close. This means that for some metric D that captures distributional proximity, they want to make sure that the distance of Fj and Fj prime according to D is at most a psi value. Examples of such a metric D can be the total variation or the KL divergence. Another point that I forgot to mention about this work is that they assume that the distributions Fj and Fj prime for the distributions Fj for the points are independent. Now, although this is really an interesting work in terms of how it incorporates stochasticity in individual fairness, we believe that there is a significant modeling issue to it. And this becomes evident when we think of what happens when both Fj and Fj prime for 2 points are the, let's say, the uniform distribution over S. So in that case, according to that paper's definition of fairness, we have achieved absolute fairness. And why? Because the two distributions are the same, so obviously the statistical proximity is 0. So we have achieved absolute fairness, but if the set S is relatively large, then this means that at the end of the day, the probability with which we will assign J and J prime to different clusters will be close to 1. Hence, the final outcome separates the 2 points, J and J prime, with high probability. And this is unfair treatment. This is unfair treatment because with high probability, you separate the 2 points, which means that they receive different quality of service. On the other hand, our model manages to resolve this issue by asking for a distribution D over assignments and not for an assignment distribution for each point. And by doing that, we are basically able to bound the quantity that really matters, which is no other than the actual separation probability. I hope this point is clear why this is an issue. The model of Anderson et al. has a problematic issue. Okay. So now let me move on to our main result. A bit of notation here. So let Pk be either K-center, K-median, or K-means. So Pk is basically the standard clustering problem, the vanilla clustering problem. Sometimes I will refer to it as the unfair problem because in Pk we impose no fairness constraints. Well, Pk BSP now will represent the variant of Pk that also incorporates our BSP constraints. So basically, Pk BSP is the problem we aim to solve. Our main theorem now says the following. If tau star is the optimal value of a Pk BSP instance, and alpha is the best known approximation algorithm for Pk, for the vanilla version, then our approach will choose a set of locations Sk, and it will construct an appropriate distribution D over assignments, where these assignments will be using the locations of Sk, such that we chose at most K locations. We can efficiently sample an assignment from the distribution D. The probability with which a randomly drawn assignment separates 2 given points will be at most Y the provided psi value for the 2 points. And finally, the objective function cost of our outcome will be at most alpha plus 2 times the optimal one. And at this point, note that because for all K-center, K-median, and K-means, we have small constant factor approximations, then we will also get a small constant factor approximation for the fair variant of the problem, because a small constant factor approximation for K-center, K-median, and K-means means that this term alpha here will be some constant factor, so we get constant factors as well. So this is a result. Now I'd like to discuss the high-level idea behind our framework, and for those of you that are familiar with the fair clustering literature, you'll see that we follow more or less a standard approach in how we attack the problem. So the high-level description of the algorithmic framework is the following. The framework works in 2 steps. In the first step, we simply use the best known approximation algorithm for Pk, and as a result, we get a set of locations SPK. So, okay, basically what we do here is the following. We have an instance of the fair problem, and we choose to completely disregard the fairness constraints and solve the problem as if it was the standard vanilla clustering problem. That's why we use an approximation algorithm for Pk. Okay, that's the first step, which is conceptually the easiest one. The second step, which is the more complicated one, constructs the appropriate distribution D over assignments, and these assignments will be using the locations of SPK that we computed in the first step. Excuse me. Now, in the second step, which, as I've said, is the more complex one, we begin by setting up a linear program, an auxiliary linear program, that tries to model an assignment problem. And what we saw in the paper is that the fractional solutions of this linear program satisfy some very, very useful properties. And given those properties, we are able to use a randomized rounding process from a paper of Kleinberg and Tardos. And okay, so when we use the rounding, we round the fractional solution to an integral one. The integral solution will basically be an assignment of the points of C to the locations of SPK. However, the internal randomness of this rounding procedure is what at the end of the day will yield the distribution D with the desired properties. So this is the high-level description of the framework. Let me now go into some more detail on how the framework works for the k-means objective function. Okay, first step, it's pretty straightforward. Just run the best known approximation algorithm for k-means, and you get the set of locations SPK. Some more notation here. Let tau k be the cost of the k-means objective for the set of locations SPK. So basically, tau k is the unfair cost. And to compute that, you simply assign each point to its closest location in SPK. Now, second step, I told you that we begin by setting up an auxiliary LP. This is the auxiliary LP, and let me walk you through it. The high level idea behind the LP is that it tries to assign the points of C to the locations of SPK. So this variable xi, j here denotes whether or not point j is assigned to location I. Given that, you see that the objective function of the LP corresponds exactly to the k-means cost. The first constraint of the LP simply says that for every point, you should assign it to one location of SPK. And now to interpret the next three constraints, let us focus on the integral version, where all variables are either 0 or 1. So in that case, for a given pair of points C, so we use C to denote a pair of points J and J prime. For such a pair E, the variable ZT, I will be 1 if and only if exactly one of the 2 points is assigned to location I. So if we sum for a given pair, if we sum over all locations of SPK the variables ZT, I, and also divide by 2 so to avoid double counting, we get the variable ZT that will be 1 if and only if the 2 points are separated. Okay, so basically ZT is an indicator variable for whether or not we separate J and J prime in the final outcome. Okay, that's for the integral case. For the fractional case, with a bit of busy work there, you can prove that ZT will actually be a lower bound on the probability that J and J prime get separated. So we can also add this constraint to the LP that says that the ZT value for every pair should be at most the psi value. So this is the linear program that will guide our solution. Okay, someone now may naturally ask why is this LP even useful? And this is a good question because, okay, if we were using, if in the LP, instead of the locations SPK, we were using the optimal set of locations, optimal for the fair problem. If we were using that, then yes, that LP you can show that it is a valid relaxation of the problem. But why now that we're using an arbitrary set of locations given to us by some random approximation algorithm? Why now the LP is useful? Well, as it turns out, we are able to prove this property here, which actually was the proof of this property was actually the most technical part of the paper. And this property says the following, that there exists a fractional solution to the LP, and let this solution be x bar comma z bar. So there exists such a fractional solution whose LP cost is at most twice the optimal one plus tau k. And the idea behind the proof of the statement is the following. It's a constructive proof. So you start with the optimal set of centers, the optimal set of locations, S star. And what you try to do is take the assignment, the optimal assignment to those centers and relocate it to the locations of SPK in a way that doesn't blow up the objective function value by too much. So the cost for S star is tau star, and we go from tau star to 2 times tau star plus tau k. So we don't have a huge blow up. And in the end, when you're done with that relocation, the final solution is basically the fractional solution x bar comma z bar. And why is this property now useful? Because we can bound the cost of the optimal LP solution through that. So the optimal LP solution, which I call x hat comma z hat here, will have a cost obviously less or equal than the cost of the solution. And so its cost will also be at most 2 times tau star plus tau k. So what you need to remember from this slide is that we have a bound on the cost of the optimal LP solution, and that bound an upper bound, and that upper bound is 2 tau star plus tau k. Now moving on to the randomized rounding, I told you that we are gonna use a rounding procedure from a paper of Kleinberg and Tardos, a randomized rounding procedure, and that procedure will round the fractional solution to an integral solution. Obviously, the integral solution is a deterministic assignment, an assignment field, let's say, that assigns its point 1 location in SPK. The properties now of this rounding that are useful for us are the following. The first says that the probability with which we separate a given pair will be at most twice the ZT value of the pair. And the second property is that the probability with which a point J will get assigned to a location I is, yes, this probability will be exactly the xi comma j value. And the probabilities here are over the randomness of the rounding. The first property basically immediately gives us the guarantee we want on the BSP constraints. Why? Because the probability with which we separate this pair is at most 2 times the ZT value, but we have an LP constraint that says that the ZT value is at most the psi value, so that's exactly what we want. And now if we combine the second property with the bound we have on the cost of the optimal solution, then we see that the expected cost of our solution will also be at most 2 times tau star and tau k. And the observation that concludes the proof now is that tau k is at most alpha times tau star. And why is that? Remember what tau k is. Tau k is the value of the unfair solution given to us by the run of the approximation algorithm in the first step of the algorithm. Okay, that was an alpha approximation algorithm. So its value tau k is at most alpha times the value of the optimal unfair solution. And the value of the optimal unfair solution is obviously a lower bound for the value of the optimal fair solution. And tau star is that value, the latter value. So we get this. And if we combine this inequality with the previous one, we see that our final approximation ratio is alpha plus 2. And this concludes how our framework works for the k-means case. For the k-median case, the framework works more or less exactly the same. For the k-center objective, you need to handle that a bit differently. But again, the high-level idea is the same. So basically, all the arguments that I showed you here apply there. In the k-center case, you just have to be a bit more careful at some points. Okay. Now I'd like to switch gears a bit and talk about something that is not really related to fairness. Okay, for that, think of what will happen in our model when all the psi values are 0. In this case, the constraint we must satisfy for every pair of points should be that the probability with which we separate the 2 points should be at most 0. So we should never separate the 2 points. So we should always place the 2 points in the same cluster. Well, this type of constraint, which is called the must-link constraint, is actually already known and extensively studied in the semi-supervised learning literature. So you see here that our BSP constraints actually constitute a generalization of the already known mastling constraints. And more importantly, our framework is actually able to provide results that satisfy exactly those constraints. And why is that? Recall the guarantee we gave on the BSP constraints. That was that the probability with which we separate a given pair is at most twice the psi value. But if the psi value is 0, then we never separate the 2 points, so we satisfy exactly their mastling constraint. Yes, our framework satisfies those constraints exactly. And now for the case-center objective, the resulting algorithm coming from our framework actually constitutes an improvement over the previous best known result for that problem. And for the k-median and the k-means objectives, the resulting algorithms are the first with provable theoretical guarantees. So pretty cool. In addition, for the case-center objective, we provide one additional algorithm that is a 2 approximation algorithm. So if I recall correctly, the algorithm that comes directly from the framework is either a 3 or a 4 approximation, but we give an additional one that is a 2 approximation. And that 2 approximation algorithm is theoretically optimal in the sense that this ratio 2 is the best possible unless P equals MP. And I'd like to discuss briefly the high-level idea behind the 2 approximation algorithm. Well, first of all, notice that the mastling relation is transitive. So if you have a mastling constraint for points A and B and a mastling constraint for points B and C, then this basically means that points A and C should also be placed in the same cluster. So given this observation, you can create groups of points that all of them should be placed in the same cluster. And our idea here, the crucial idea that we used here was that if you treat these groups as a single point, if you treat each such group as a single point in one of the standard case-center algorithms, then through a series of lemmas and theorems, you are able to show that this suffices in order to get the 2 approximation algorithm. So that's all I wanted to say with regards to mastling constraints. Some additional results now that we got in the paper. Well, we noticed that our framework can also handle more intricate constraints on the set of chosen locations. So far, I have only talked about a simple cardinality constraint, so you should choose at most k locations. However, we are also able to handle knapsack or matroid constraints. In a knapsack constraint, the locations each location has a cost associated with it, and we are also given a budget. And the constraint there says that the total cost of the locations you choose should be at most a given budget. In a matroid constraint, the set of chosen locations should be an independent set of some given input matroid. So yes, we are able to handle those constraints as well. And basically the only change that you need to perform is in the algorithm you use in the first step of the framework. So for example, if you have an algorithm for, let's say, knapsack median, you can use that algorithm in the first stage to solve knapsack median BSP. Okay, and the guarantees we got on those were again similar. A 2 violation for the BSP constraints and an alpha plus 2 approximation ratio. Now, being able to handle more intricate constraints made us curious about this question here. What if we have no constraint at all on the set of chosen centers, on the set of chosen locations? What if the only constraints of the problem are the BSP ones? At first, you might wonder if this is actually an interesting and difficult problem, because in a standard clustering problem, if you have no constraint at all in the number of centers you can choose, then you pick everything as a center, you get an objective function value of 0, and everyone's happy. So is this really interesting? Well, as it turns out, it is, because the resulting problems are NP-hard, even regardless of the objective function. So for all 3 objective functions, k-center, k-median, and k-means, we get NP-hardness results, which basically shows that the BSP constraints are enough to make the problem NP-hard. And that's on the negative side. On the positive side, we showed that a modified variant of our framework can yield results that can yield a solution that has cost at most the optimal one. And again, in terms of the BSPs, we provide the same guarantee that we separate any two given points with probability at most their provided psi value. Okay, now let me discuss the experimental aspect of our work. For one thing, we compared our algorithm against the results of Anderson et al. And against our previous algorithm. And the metrics we focused on for the experiments were the violation of Fairnes constraints and the objective function value, obviously. What we observed was that our algorithm in most cases outperformed previous results. And here I'm just going to show you the experiments, the comparisons against the Anderson et al. Paper. Regarding our setup, we used 3 datasets from the UCI ML repository, namely bank, adult, and credit card. And from each of them, we subsampled 1,000 points. For the experiment, I'm going to present here the objective function chosen was the k-means one. And so in the first step of the framework, we used Lloyd's algorithm. As on to how we constructed the psi values for the BSPs, we basically used 2 approaches that are found in the Anderson et al. Paper, and I'm going to discuss those 2 approaches in more detail later. Okay, now both our algorithm and the Anderson et al. Algorithm involve randomized assignment procedures. So what we did is what we did in order to estimate the empirical separation probabilities and the costs was just running 5,000 trials of each such process and computing these values here simply by taking averages. For a pair of points, we considered its fairness constraint to be violated if the empirical separation probability that we computed over the 5,000 trials, if that was greater than the true one, and the true one was just psi value, if it was greater than the true one by some small amount epsilon, which we set to 0.05. And finally, for the comparisons regarding the objective function, what we did was take the average cost over the 5,000 trials for its algorithm and divided that by the cost of the solution given to us by Lloyd's algorithm. And we did that because this cost is a good estimate of the optimal unfair cost. So basically, this ratio here corresponds to an empirical estimation of the price of fairness for the algorithms. Now, how we constructed the psi values for the BSP constraints. I told you that we used 2 approaches from the Anderson et al. Paper. We wanted to be fair with regards to our comparison with that paper. So that's why we used their approaches. In the first approach, which is the simplest one, what we basically did is we scaled the metric space linearly so that all pairwise distances are in 0, 1. And so you can interpret these distances as the separation probabilities. So we set the psi value for a pair to be the distance of the pair. But we only did that, we only included pairwise constraints between each point J and its closest 100 neighbors. We didn't include all possible pairwise constraints. Again, that's what the Anderson et al. Paper did. In the second approach, we did something slightly more intricate. For each point J, we first computed this value Rj, which is the minimum value such that at least C over K points are within distance Rj from J. And then for the psi value, we did the following. For every point J prime that was within distance Rj from J, we set the psi value to be the distance of the 2 points over Rj. Okay, here you can see our results with regards to the first way of constructing the psi values. Our algorithm is denoted as our alg, and the algorithm of Anderson et al. Is denoted by algif. In the first table, you see how we did in terms of the percentage of violated fairness constraints, and you see that our algorithm does significantly better, and actually Anderson et al. does bad. Okay. In the second table, you see the comparisons with regards to the price of fairness. Here, there is no clear-cut winner. I mean, there are situations that we do slightly worse. There are situations that we do slightly better. But overall, the two algorithms are more or less the same. And here are our results for the second way of constructing the psi values. Again, you see that for the percentage of violated fairness constraints, we do much better. And again, for the price of fairness, both algorithms do pretty much the same. So there is a clear pattern when it comes to violation of fairness constraints. We do much better. For the cost of the objective function value, for the k-means cost, both algorithms are pretty much the same. And you can also see that all values here and here are small constants. So even in terms of the empirical estimation of price of fairness, we do good. So we're close to the optimal and fair, let's say. So that's all I had to say. Thank you for attending. I'm glad to take any questions now.
Any questions from the audience? Just to repeat what Leo said. So Leo, can I add some perspective to this? And you of course, feel free to add to it. So, if I can give a plug to a broad approach to fairness that, we have been taking, John, myself, Leo, Syed, and a variety of other collaborators, it is, one such thread is what one may call probabilistic individual fairness. So basically, so recall that, when Leo talks about distributions over assignments, what he basically means is a randomized assignment algorithm, right? So the broad, philosophy here is to, on the one hand, guarantee some global properties with probability 1 or with high probability. For example, in all of the examples that Leo gave, the number of clusters outputted is at most k with probability 1, right? So in other words, in every run of the algorithm, that will be true, right? On the other hand, you want to balance that with something at an individual level, which is necessarily probabilistic, because of course, in resource allocation problems like this, you cannot satisfy everybody in general. So rather than discriminating arbitrarily against some people and systematically only giving it to some subsets of the people, what you're guaranteeing for every individual, or in this case, every pair of individuals, because the Psi is defined over pairs of individuals, is a certain guarantee on the probability of their quality of service, right? So, this can be interpreted in two ways. One is, again, like Leo said, if you're running this algorithm many times, then of course, just the frequentist interpretation of probability will tell you for every individual, or again, every pair of individuals, that on average, their quality of service over this repeated run of such algorithms would be quite good, while the worst case behavior will never be bad, right? So we have some probability 1 worst case guarantees and some average case guarantees at an individual level. But there is a way to, even for one-shot algorithms, by simple applications of the laws of large numbers, these things can be translated into verifiable fairness, basically. So this is just one approach to fairness. And as all of you know, there are multiple ways to define, to model fairness, and it's a very active area. Leo, sorry for speaking for so long in the middle of your talk or at the end of your talk, but what I wanted to say is, we'd be very, speaking for myself, we'd be very glad to get feedback about, this kind of approach. If anybody has thoughts about improved formulations or related formulations, or literature that we may not know, we'd be very glad to chat with you. I thought I'll kind of take over the session. Leo has been doing a very good job of running the series. Because Leo is the speaker, I thought somebody should introduce him. So thank you again, Leo. If there aren't any other questions, we can stop here. Okay, there don't seem to be questions. So Leo, thanks again. And for the audience, of course, keep in mind that we'll have this series, at least for this semester, but even perhaps for the whole year. So do keep attending. And we would also love to have talks from talks from many of you. So please do let Leo know if you'd like to give a talk. Thanks again.
Bye, everyone.
Bye.